Hello everyone, I'm Qiuyu from Carnegie Mellon, and I'm excited to present our work, the Fluidic Computation Kit. Before I begin, I'd like to express my gratitude to the team who worked with me to bring this project to life, including Haiqing and Yijie from Tsinghua, Qiuyu from Carnegie Mellon, and our group leader, Linen. Mechanical mechanisms have been used by our ancestors to process information since ancient times. Even until the last couple of centuries, scientists continued to study mechanical computing devices, such as analytical engines. In the information age, electronic forms of computation have overtaken these mechanical forms. For example, in human-computer interaction, embedded electronic chips are now widely used as the computational units for prototyping physical computing interfaces and devices. However, there is a recent trend towards exploring unconventional forms of computation. For instance, researchers have developed fluidic computation structures which have been integrated into microfluidic chips and robots. While fluidic computation has demonstrated success in various science and engineering applications, its adoption within the human-computer interaction community is still in its early stages. Pneumatic or hydraulic interfaces have been extensively investigated in the past decades. A lot of work has contributed to greatly expanding the actuation, sensing, application, and user experience evaluation. However, the control aspect of these interfaces has received little attention. As a result, many of these interfaces are still controlled by bulky valves and electronic boards. Two works from last year made a good start by introducing some fluidic computation structures based on the beam deflection mechanism. However, these structures can only enable the basic logic gates, and they have a poor cascadability and very limited computational complexity. To address this gap, we introduced the Fluidic Computation Kit, which provides a rich set of libraries for prototyping fluidic computation devices. It covers all the way from multiple elementary components to various high-level operators, including 4 types of elementary components, 6 categories of computational operators, and some complex circuits examples. In addition, with the help of airbags, we can easily detect air pressure changes induced by different types of force. These air pressure signals can then be taken and processed by the fluidic computation circuit. The computation results are delivered in the form of airflow, which can be utilized for various output modalities. In the next, I will provide a detailed explanation of this diagram, starting from the components. The switch has 2 channels, separated by an elastic membrane. The lower control channel can push the membrane against the upper wall to block the target channel. And to ensure that the valve can be closed even when the air pressure in the control channel is lower than the air pressure in the target channel, we added a pair of magnets. A single switch can function as an inverter, also known as the NOT gate. It can invert the inputs. In our system, high pressure corresponds to 1, and low pressure corresponds to 0. And here we demonstrate the cascadability of the switch by connecting 2 in series. This configuration inverts the input twice, resulting in the input being retained. While this structure may not have a direct application, it can be used to restore the air pressure when the system is scaled up. The diode is a check valve. It will only allow fluid to flow in one direction. The resistors are components with various long, narrow channels with high flow resistance. It can be used to control the flow rate, pull up or pull down the air pressure. The capacitor is a versatile component and plays a critical role in many operators. It consists of a triangle adapter and a relatively large deformable chamber. Different kinds of chamber can be adapted to achieve different functions. For example, as a buffer, storage, etc. Now let's move on to the operators. As depicted in the figures, basic logic gates can be constructed using switches and resistors. Here is an application example of a posture detection and correction chair. The chair has two airbags embedded in the cushion to detect force distribution, a fluidic computation module constructed by logic gates, and two airbags mounted to each side of the chair to provide output feedback. The device will remind the user to maintain a good sitting posture. Additionally, the output airbag will remain uninflated when the user is not sitting in the chair. The output flow rate of the filter is dependent on the frequency of the input force. Changing resistor R and capacitor C can regulate the peak frequency. We developed a force encrypted latch based on a filter, with the force frequency as input and the deformation at the output. The door can only be opened if the user squeezes the door handle at the correct frequency. The timer will delay the signal transmission for a specific period of time, which can be regulated by adjusting capacitor C. We utilized the timer to create a self-contained wake-up alarm. It is powered by the pressurized air inside the pillow generated by the weight of the user's head. As shown in the footage, after approximately 5 minutes, a refreshing breeze will wake up the user from the nap. A register is a storage unit that can hold 1 bit of input force data. In addition to a data pin, it also has an enable pin to control when data can be overwritten. The multiplexer can direct the input signal to any of the 2 to the power of n outputs by applying all the n input controls. An edge detector can monitor the rising or falling edge of a signal and produce a short high-pressure air pulse at the output. We constructed a 2-bit parallel processor using the aforementioned operators. The processor can accept various types of force inputs, as shown in the top left corner of the diagram, and produce deformation at output. We also developed a game that utilizes this processor. The rule of this game is player A will tap the airbag button in front of her, and the player B and C need to respond quickly by tapping their buttons as well. Okay, now let me explain how the processor works. Whenever player A taps her button, the edge detector will generate a short signal 1. This short signal is then inverted by the NOT gate to 0. And this short signal 0 is fed to the control input of the successive registers, enabling the registers to receive data while this short signal 0 lasts. If player B and C hit their buttons timely, 1 will be written and stored at the register. Otherwise, 0 will be written and stored. Lastly, a successive demultiplexer will decide which balloon should be inflated based on the stored data in the registers. Now let's enjoy the game. So this is our work, Fluidic Computation Kit. While semiconductor-based electronics are powerful, we set out to explore how fluidic computation can supplement or augment electronics when it comes to designing physical and material-based interfaces. Looking forward, electronical-free and electricity-free interfaces based on mechanical computers could help us build sustainable and lower-powered devices. For the future work, we are considering investigating large-scale production to allow people to buy the fluidic computation components, just like how they purchase electronic components or Lego pieces, so they can learn, build, and play with fluidic computation interfaces. And we are also thinking about exploring more input modalities and other actuation methods and energy sources, etc. Please refer to our paper for details on the operator's functionality, fabrication process, experiments, evaluation result, applicability, and more. Thank you.